Welcome to complex analysis. Imagine you are driving a car and you only have a record of your speedometer readings over time. But you want to know your exact location on the map. Finding your location from your velocity is exactly like finding an antiderivative. Today, we will learn how this simple reverse process allows us to calculate the total accumulation of a function along a winding path without actually having to walk the path step by step. Now that we understand the goal, let us define this formally for complex numbers. Suppose we have a continuous complex function, little f of z, defined inside a specific region or domain. A domain is just a connected, open patch of the complex plane where our function behaves nicely, without any sudden breaks or holes. A big function f of z is called an antiderivative of little f of z in that domain if the derivative of big gives us back our original little f. To explain it twice, if you differentiate the big parent function and get the small function, then the big function is the true antiderivative of the small one. This definition leads us to an incredibly powerful shortcut. Why do we care about finding this parent function? Because it makes integrating along a curve known as a contour incredibly easy. This formula says that the integral of a function along any path between 2 points is simply the antiderivative evaluated at the end point minus the antiderivative evaluated at the start point. The actual winding path taken completely disappears from the calculation. This means the integral is path independent. If the starting point and ending point are the same, the total accumulation is just zero, no matter how wild the journey was. Before we move on, let us see this with a concrete visual. Look at the diagram on screen. We have a starting point Z1 and an ending point Z2. You can take a straight blue line, a zigzagging green path, or a wild red loop from the starting point to the ending point. As long as the function has an antiderivative in the region containing these paths, the total accumulated value will be exactly the same for all three routes. This property is called path independence. It means you never have to worry about the messy details of the journey, only the destination and the origin. Now that we have our formula, let us build confidence with a basic numerical example. We want to evaluate the integral of the function 3z squared along any contour. The starting point of our journey is the origin, where z equals 0. The ending point is the complex number 1 plus I. Instead of parameterizing a specific path, we will use a new shortcut. First, we find the antiderivative. By reversing the power rule for derivatives, we know that the derivative of z cubed brings the 3 down and drops the exponent to 2. Therefore, z cubed is the correct and valid parent function. Continuing with our problem, we apply our fundamental theorem of calculus for complex integrals. We take our antiderivative function, z cubed, and prepare to evaluate it at the final destination point, 1 plus I. We then subtract its value at the starting point, 0. Substituting the actual complex numbers into our formula makes our lives very easy because the starting point simply evaluates to 0. This means we only need to calculate the cube of the complex number 1 plus I. The problem has now been reduced to just basic complex multiplication. Let us finish the arithmetic. To cube the number, we first square it to break the math into smaller steps. Expanding 1 plus I squared gives 1 plus 2I plus I squared. Since the imaginary unit squared is negative 1, the real numbers cancel out, leaving just 2I. Finally, we multiplied this squared result by one more factor of 1 plus I. Distributing the 2I gives 2I plus 2I squared, which simplifies to negative 2 plus 2I. We found this exact accumulation without ever needing to know the actual shape of the path traveled. Now that we have successfully used this formula, let us understand where it comes from by proving it step by step. First, we write the contour integral using a parameter t, which acts like time, running from a start time a to to an n time b. The term z prime of t represents our velocity. Next, we use the chain rule from basic calculus on our nested function. Because we defined big F as the antiderivative, we know its derivative is exactly equal to little f. Notice that the right side of this chain rule equation perfectly matches the inside of our integral from the very first step. Let us bring it all together. We substitute our chain rule result back into the original integral. Now we are integrating the exact derivative of a function with respect to time t. The complex path has been completely absorbed into a simple rate of change. By the standard fundamental theorem of calculus for real variables, integrating a rate of change over time just gives the total net change from the start to the end. Here, z of b is our final position z2 and z of a is our starting position z1. This proves our magical shortcut is mathematically sound. So, we have proven that path independence holds, but there is a catch. Let us look at why the domain matters so much. Not all functions have a single, well-behaved antiderivative everywhere in the complex plane. For example, the antiderivative of 1 over z is the complex logarithm. However, we must be extremely careful because this function has a branch cut, which is a line where the function suddenly breaks and is no longer continuous. For the principal logarithm, this dangerous break happens along the negative real axis. To use our shortcut, our path must stay entirely within a safe domain that avoids this cut. This brings us to the formula for the principal complex logarithm, which perfectly reverses the derivative of 1 over z. The formula has two parts. The first part is the normal real natural logarithm of the absolute value of z, which is just the distance from the origin. The second part is imaginary, using the principal angle of the complex number, measured in radians from negative pi to positive pi. If the distance from the origin increases, the real part grows. If the complex number rotates around the origin, the imaginary part changes. We can use this as long as we do not cross the negative real axis. Let us see this in action with a slightly more complex example. We want to evaluate the integral of the function 1 over z. The contour goes from a starting point of negative I to an ending point of positive I. We are told we must stay entirely in the right half of the complex plane during this journey. Because our path stays in the safe right half plane, we avoid the branch cut entirely. We can safely use the fundamental theorem of calculus. We plug the ending point and the starting point into our logarithmic antiderivative function. Now we just need to evaluate these two logarithms. Continuing our calculation, we evaluate the logarithm at the ending point, positive I. The distance from the origin to I is exactly 1, and the natural log of 1 is 0. The angle pointing straight up to I is 90 degrees, which is exactly pi over 2 radians. Therefore, the logarithm of I is purely imaginary, giving I times pi over 2. Next, we evaluate the logarithm at the starting point, negative I. The distance is again 1, so the real part remains 0. The angle pointing straight down to negative I is negative 90 degrees, which is exactly negative pi over 2 radians. To finish the problem, we subtract the starting value from the ending value. We take I times pi over 2 and subtract negative I times pi over 2. The two negative signs cancel out to become a positive sign. They add together perfectly to give a final answer of I times pi. This beautiful result shows how complex angles directly influence the outcome of an integral. The physical meaning here is that as we rotated from the bottom of the complex plane to the top, we accumulated exactly half a circle's worth of angular change, represented by the pi. Before we conclude, you might wonder why this matters in the real world. Without antiderivatives, engineers and physicists would have to manually calculate the accumulation of forces along incredibly complex, winding paths. In fluid dynamics, complex functions are used to model the flow of water or air around obstacles like airplane wings. The integral of these functions helps determine the total circulation or lift generated by the wing. By finding an antiderivative, an engineer can calculate the total lift just by looking at the boundary conditions, completely ignoring the chaotic, swirling paths of individual air molecules in the middle. Let us review the key takeaways from today's topic. First, an antiderivative is simply the reverse of a derivative, acting as a parent function that reveals the total accumulated change. Second, when a complex function has an antiderivative in a specific region, its integral between 2 points is completely independent of the path taken. You only need to evaluate the parent function at the final destination and subtract its value at the starting point. Finally, always be mindful of the domain, especially with functions like logarithms that have branch cuts. You have now mastered the absolute cornerstone of solving complex integrals quickly and elegantly.